Hello again, everybody. This is part 2 of our notes on section 4.2, trig functions and the unit circle. At the end of our last video, we talked about the unit circle itself and figured out how we can construct it from our special right triangles. So we can get right back into our work, looking at an example using this using the unit circle. So here they tell us that they want us to find the value of all 6 trig functions if we know that the sine of theta is -5/13, with the statement that theta must lie between -90 degrees and +90 degrees. So what I did was I borrowed those degree values from our unit circle here, just from -90 to +90. So I have a sine that is negative here. I basically have to choose between quadrant 1 and quadrant 4 here. And if sine is negative, I must have a triangle that exists in the 4th quadrant. It's very important that we establish which quadrant we're working in, because that will help us create our reference angle. So if I'm in the 4th quadrant with a negative sine, my triangle must look like this with a reference angle theta here. Now I can plug in. I know that sine is -5/13. So the 13 will be the hypotenuse, and the negative comes from the y coordinate. So I'll have to use the Pythagorean theorem to find the third side, but this is a Pythagorean triple, and we'll end up with 12. The most important part of this is figuring out which quadrant we're in, because it will affect the signs of many of our coordinates. From here, our work gets pretty simple, right? I'm just finding my cosine. In this case, it is 12/13, which makes sense because if we're in the 4th quadrant, we should have a positive x value, and that's what cosine corresponds with. Our tangent value is going to be -5/12. Our cosecant is going to be -13/5. Our secant is just the reciprocal of cosine, 13/12, and cotangent will leave us with a -12/5, as it is the reciprocal of tangent. So there's some other identities that we're going to be working with extensively here. My expectation is that we've seen at least a few of these in the past. So we have our reciprocal identities. We've talked about them already today. And then we have a couple new ones. So the quotient identity here tells us that tangent theta is the same as sine over cosine. This hopefully makes some sense. If I were to set up sine as opposite over adjacent and divided it by, opposite over hypotenuse. Let me fix that. Opposite over hypotenuse and then adjacent over hypotenuse. We could simplify this fraction, right? We could multiply by the reciprocal. We'd have opposite over hypotenuse times hypotenuse over adjacent. Well, those hypotenuses would cancel. We'd be left with opposite over adjacent, which is another way of expressing tangent. So that's why this quotient identity works. And the reciprocal of tangent being cotangent will also lead us to the reciprocal quotient identity, where cotangent is the same as cosine over sine. We also have these Pythagorean identities. The one that we really want to hold on to right now is sine squared plus cosine squared equals 1. That is directly coming from our Pythagorean theorem. So if I know that my hypotenuse is length 1, if I'm on the unit circle, and here's what else I know. I know that the x-coordinate can be represented by cosine theta and the y-coordinate by sine theta. So using our Pythagorean theorem, we get sine squared plus cosine squared equals 1 squared, which is itself 1. That's where this is coming from. We'll talk more about our other Pythagorean identities as we get into Unit 5, but they also relate to other, each of them relate to other trig functions when they're squared. 1 plus tangent squared theta equals secant squared, and 1 plus cotangent squared equals cosecant squared. worth mentioning here that sine squared theta really represents sine theta times sine theta. All right, so let's look at a pretty simple application problem. Here they tell us that a ladder leans against the side of a house. The ladder makes an angle of 60 degrees with the ground. How far up does the ladder reach? Always recommend a diagram on a problem like this. Our ladder is leaning against the house. We're going to assume our wall of our house is making a 90-degree angle. This angle of elevation is a 60-degree angle. And we know that a 10-foot ladder leans against the house. Well, this is a 30, 60, 90 triangle. So again, the longest side of a 30, 60, 90 triangle is twice as long as the shortest side, and then the shortest side multiplied by √3 gets us our intermediate side. So how far up the house does the ladder reach? 5√3 feet. If this were a calculator problem on a test, I'd want a decimal approximation, but in this case, 5√3 is perfect. Why don't you guys try the next problem on your own? You have a surveyor standing from the away from the base of the Washington Monument. The diagram on the right side of your page should be useful for you. Why don't you go ahead and try this one, and we'll see how it goes. Looking at this diagram, the two sides that are important or relevant to our problem, the 115 feet away, that X quantity, and then we're trying to find the height of the monument, so that Y value. Those are our opposite and adjacent sides in reference to our angle of elevation. So if I have the opposite and adjacent, I'm going to use the tangent function. So I set up my equation as you see here. The tangent of our angle, 78.3 degrees, is y over 115. I prefer to solve for y before we plug anything into our calculator. Just makes the process a little bit quicker. So I'll solve for y to be 115 times the tangent of 78. And I can make sure that my calculator is in degree mode. And then I enter that in and find the height is 555 feet. So our last page of notes here refers to non-right triangles. Our first law, this is in regards to non-right triangles, the law of sines is the one that I would recommend leaning on whenever we can. The law of sines is useful because it sets up as a proportion the sides within a triangle. As you can see here, the side and the angle it is across from when we take its sine will be proportional whichever angle and side length we're working with. So we can set up a simple proportion and solve using the law of sines. We also have the law of cosines, which you can see here is a little bit more complicated. We can see here that involves all three sides, a squared equals b squared plus c squared, minus 2 times b c. One note about the angle we're calling A here, and the side we're calling A, it's not necessarily the longest side. It's always related to the angle that we do know about or what we're curious about. So let's take a look at this problem here. They've given us a triangle of 8 feet, 14 feet, and 19 feet. Our goal here is to solve this triangle. We want to try to find the angle measures of all three. So I'm going to set up my law of cosines. It doesn't really matter which angle we're looking for, but let's go ahead and find angle A first. So I'm going to say that 8 squared equals 14 squared plus 19 squared minus 2 times 14 times 19. Just as we're working through this, times the cosine of angle A. It doesn't really matter which place we put things. I know that this appears a little bit like an a squared plus b squared and c squared, so maybe we're thinking about the Pythagorean theorem. But remember, that only applies to right triangles, and when we're dealing with the law of cosines, we're almost always dealing with non-right triangles. So I'm going to use this formula to figure out angle A. I'm using my calculator here. I'm going to manipulate, and I'll show you guys an intermediate step. Once I solve for the cosine of A, I got a decimal. I got 0.92669. I would use the inverse cosine on my calculator to find this angle, the angle whose cosine is this, and I will get angle A to be 22.08 degrees. I can do the same thing to find another angle. I could also use the law of sines from here, but because we have our calculators out, I don't think it's too difficult to set this up to find angle B. So we'll set this up similarly. We'll say 19 squared equals 8 squared plus 14 squared minus 2 times 14. Sorry, times 14 times 8 times the cosine of angle B. So just a little bit extra practice on the law of cosines here. We go through the same process, simplify on the right, divide, and we'll end up with a B value for our angle of 116.8 degrees. Well, if I have two angles in a triangle, I really have three. So that means I could subtract these two angles from 180 degrees, and I would find that angle C equals 41.12 degrees. So we solved this triangle. We now have all the sides and all the angles. There are 3 word problems here. If we were doing this in class, I would let you guys try this as best you can. Obviously, if you're unsure, keep watching and I'll keep explaining. But I definitely recommend pausing now and try to work through these 3 word problems and see what you can do. All right, let's finish these up. So on number 1, we have 2 planes leaving an airport at the same time, one flying west and the other southeast, and they are flying for 2 hours. So I took those speeds, 500 and 300, and doubled them and made those the side lengths of my triangle. I connected those endpoints to find the straight line distance between these 2 planes. So I set up, I didn't have enough information really to get at a law of sines problem here, so I had to use the law of cosines. I figured out that the angle was 135 degrees, right? From due west to due south would be 90, and then halfway between south and east would get us an additional 45 degrees, leaving us at 135. Well, I plugged that into the law of cosines and let my calculator do the heavy lifting. I find that my answer is 1,486.11 kilometers. On number 2, they tell us that we have a isosceles triangle where each leg is 27 centimeters and each base angle is 23. So I drew a picture, labeled what I knew. I knew that my base angles were 23, and that top angle, the non-base angle here in this isosceles, must be 134 degrees. Well, now that I have all the angles, I can use my law of sines. It's a little bit quicker. So I set this up as a ratio. My recommendation is to set your ratio up so your unknown is always kind of in this top left location, right? Because we always have a fraction equaling a fraction in these law of sines problems, we can flip our numerators and denominators as long as we're doing it consistently. So the math of it becomes a little bit easier if my unknown is in that top left location. So I manipulated this equation. I multiplied both sides by the sine of 134 and then divided by the sine of 23. Sorry, I really cross-multiplied and then divided by the sine of 23. And ultimately, I found that the side length was 49.71 centimeters. All right, let's take a look at this last problem. They tell us that we have 2 sides of a parallelogram, and their lengths are 50 and 80, just highlighting my diagram as we go. They tell us that one diagonal is 90 centimeters, and we need to find the other. So that green diagonal is really what we're looking for. So the first thing I want to do is I need to figure out I need to use the information they give me to figure out something about an angle here, right? So if I want to find a side length and I have an angle, the law of cosines is opening up to me. So where I'm going to start is I'm going to start by actually finding an angle that I can find, angle C. So we're really using, let me remove some of this highlighting so you can see exactly what I'm saying here. So if we focus on angle C here, we're really looking at this triangle where I know all three side lengths, 50, 80, and 90. So I use my law of cosines to find angle C. And I found that angle C was 84 degrees. From here, I'm going to lean on some geometry knowledge and remembering that consecutive angles in a parallelogram are supplementary. So I know that angle A here is 180 minus angle C, in other words, 95.74 degrees. So where we go is we end up looking at a kind of nested triangle, right? One that lays on top of that green one. But here, our missing side, this diagonal here, is what we're looking for. So now I have an angle and two sides. I can use the law of cosines again and find that side length. I'm calling A here. It's across from angle A. Again, I'm using law of cosines. I plug in and find that length is 98.49 centimeters. And we are done. Thanks, everybody.